Hello my friends, Sharky here, and today I'm going to give you guys a quick show and tell on this 2 transistor air-cooled LDMOS unit. So it's still not done, still waiting on parts, but it's 99%. I just need to plug this hole and then put a over temperature switch inside of there somewhere. Ordered the wrong ones, I got the normally open ones instead of the normally closed ones, go figure. But yeah, this is it. Nothing too fancy looking on the outside. I mean, I lasered these cool little acrylic cutouts. Those came out pretty nice. But yeah, we'll pop it open and take a look at inside in just a moment. But for now, let's watch the meter swing, because that's always fun. Right now I'm running it on this this here switching power supply. It's set at 65 volts. And a word of caution: 65 volts is kind of a lot for the air-cooled pallets. It's kind of a lot, man. Running the air-cooled pallets on 65 volts is like, you know, it's like a comp box where it's a lot. You're kind of pushing the limits there. So if anybody wants to, you know, anybody that's building with these air-cooled pallets, just keep that in mind. 65 volts is kind of a lot for the air-cooled pallets, and you can run it for a moment or so, but it's too much. And because of that, this is not the power supply that I'm going to be using with this box. I built a linear power supply that we'll take a look at as soon as I'm done showing you what the meters do. We'll plug that power supply in, which is a little lower voltage, and I'll show you what the meters do then. But let me give you a quick run around. So this here bird meter is connected to that line section over there. 5,000 watt slug, dummy load off this way, and that piece of coax is coming back over here to the output of the amp. Input of the amp is coming through this coax through the LP100A RF sensor. So input power is going to be on this guy up here. I'm driving it with this radio. This is like my usual bench radio. It's a stock radio, other than it's got a motor mouth modulator board in there, so I can vary the peaks. That's really the only feature of the modulator I'll be using, is just varying the peaks up and down. Actually, I'm going to leave them right where they're at because it's already set just right. Let's kick on the old power here. All right, so right now this meter is in bird average, 5,000 watt slug. So we got our 1,000 watt dead key. Let's turn on the modulation. Okay, that's our bird forward swing. And in peak mode, a little over 4K. So there's our modulation on the oscilloscope. Looking pretty good. There's our carrier power. And there's our peak power. And you can hear the fans kicking on over here. They're on a temperature switch, so they kick on and off as they please. But yeah, that's what she'll do on 65 volts. My input drive was about 18 watts. I could have given it 2 more watts and gotten, you know, a little tiny bit more power out of it, but probably wouldn't have gotten much, so no big deal there. Spectrum analyzer. I don't know if this is gonna work because this little freaking attenuator has an issue, but let's try it anyway. Let's see what it'll do. This is kind of tough one-handed. Hey, it worked. Check that out. So there's our spectrum. Nice and clean, clean, clean. Looks pretty good to me, man. Looks pretty good to me. That's so that's what it'll do at 65 volts. Let me grab the other power supply. We'll plug it in and take a look at the meters and see what we get. This here is the linear power supply that I built for this box over here. It's got 2 Antec toroidal transformer power supply modules in it. We'll take a look at it in a minute, but most important thing is it weighs a ton, dude. This thing is heavy, and it sucks, but it's clean linear power. Don't have to worry about any kind of scratchy nonsense in your receive. So got it connected to our Anderson clip here. And like I said, this one runs a little bit lower voltage. It rests at about 65, so it sags down below that when you key up and modulate and all that stuff. I don't know exactly what it gets to, but I think it rests, or it drops down to about 60 volts under load. That's just a ballpark estimate. Let's take a look at the meters and see what they say. Okay. Okay, so there's our 1000-watt carrier. Let's modulate up. Okay, still got a little bit of forward swing, just like we did before. Let's turn on the peak kit. Modulate forward. Okay, so a little shy of 4K. That's not too bad. So with the linear power supply, we lost, I don't know, 300-400 watts off the top end, which is no big deal in my opinion. I wouldn't cry about it, that's for sure. And the air-cooled kits are, like I said, you run them at 65 volts, they're kind of, in the danger zone. Well, running them a little bit lower is definitely better for longevity. It's better for key down time. You're not going to hit your temperature limit nearly as often. So realistically, this box should be running right around 50 to 57 volts. But I'm not long-winded, so I'm not going to stay on the mic all day long. If you want to stay on the mic all day long, you can. You just got to run a box like this at like 50 volts so it doesn't overheat. But yeah, let's pop open the lids and take a look inside. These are the Antec modules that I showed in a previous video, and they've been really great. I haven't pushed them to their limits, but they seem pretty durable. They use 2 of those bridge rectifier modules per transformer. 2 10,000 puff or 10,000 microfarad capacitors per transformer, so we got 4 of those, and then I got 2 additional ones here in the back. As far as the power supply goes, there's nothing terribly fancy going on, just some red and black wires all kind of going into the same place, and then a pair of fuses running our 240 volt power up to a switch, and that connects the transformers, and that's about all there is to it. This was a super easy project, other than the fact that those transformers weigh, a metric ton each. But it works great, man. No complaints. The voltage is pretty stable under load. Great little units, and for the price, I don't have any qualms about recommending these for other folks. So these are the quote-unquote 63 volt ones. They're the exact same unit that was in my previous video about these, and they're a great option. If you want to build the supply from scratch, you can buy just the transformers, and you could place them in your own box however you want. Just be aware that the 63 volt supply uses the 45 volt transformer. So, see if I can get a shot of that. Where's it at? It's in here somewhere. There we go. Focus. There we go. Okay. So yeah, there's the part number on the transformer itself. You can buy these separately. I think they're about 155 bucks a piece. Or you can buy the whole unit for $210. So one whole power supply with the boards and everything is $210. But yeah, they're good stuff, and I don't hesitate to recommend them one bit. But let's come over here and take a look at the box. So, first things first, this is not my finest work, but I'm still pretty happy with it. I started building this box before I even started working on my water-cooled 4-transistor box. So I went over to the rack one day where I keep all my radio junk, and I saw this sitting there and it wasn't getting any love. So I decided to pick it up, put some pallets in it, and get it done. The pallets aren't exactly where I want them. There's a few holes in places that I didn't really want them. It's not exactly how I would want it, but it came out really well, and I don't have any problem with it. It's gonna run great. It's not perfect by any means, not my finest work, but man, it runs. And maybe one of these days it'll end up in my mobile. I don't know. We'll see about that. But the pallets in here are my standard Sharky 137 pallets. Really nothing special about them. There was this weird issue I was having with the linear power supply. Somehow the 60 hertz from the power supply, or the 120 hertz ripple, was making it onto the RF really badly, and it was interfering with the bias circuit somehow. So if any of you guys that are building these pallets, if you ever have an issue like that, just add a little bit more capacitance right here. So between the center tap on the input transformer and ground, just add a little bit of extra capacitance there. That's what I did, and it made it go away. It was still a really, really weird issue. I tried a bunch of things. I tried just one of these pallets. I tried it on the the switcher supply, I tried it on the linear supply, and nothing was happening. And it was only this particular setup where that was happening. Like maybe something about the inductor coils, or where the, you know, RF getting in somewhere. I don't know. Super strange, but putting that little capacitor right there solved the issue. So this over here is our output relay. So I like to use 2 relays in my boxes, just, you know, for redundancy. The idea behind using 2 relays is that you have 2 contacts per switch, so you have a little bit of redundancy. If one of your contacts gets kind of burned up, hopefully the other one's going to pick up the slack. That's kind of the idea. Bottom line is I just really hate cleaning relays, so I did it this way. And I also made it so I can clean the relays easily if I ever have to. But all my boxes are manually keyed, so I key them manually with a sequencer that turns the box on at the correct time, so that the relays don't get hotkeyed and they don't get arced over. And yeah, that way I don't have to get in here and clean my relays. My receive doesn't get all fuzzy or doesn't cut out or anything. It just kind of works. So this box has already lost a pill. It already lost a pill. And it was my fault. It was my fault for doing something really stupid. I have these jumpers over here that I made a long time ago. It was like one of my first projects that I did when I got into radio. I ordered me some RG400 and made a few jumpers. And when I soldered the PL259, I didn't do such a great job. And I think the center conductor arced inside of the connector. And all this happened while this box was running 3 kilowatts at 65 volts. So go figure on that one. And whatever happened inside that connector, it took that transistor and it shot it through the roof. The lid on that, this is obviously it's fixed now, but the transistor that was there, the lid exploded into a million pieces, and you can probably see some of the burn marks still on that resistor there. But if anybody tries to tell you that LDMOS is invulnerable to SWR issues, it's not true, man. SWR really doesn't mean anything. I was in a Facebook group the other day with some really smart people. This gentleman named Thomas, he's been working on amplifiers for a long time, and he kind of broke down the situation of, you know, SWR handling. And it has nothing to do with SWR at all. What it really has to do with is voltage and current. If you overvolt the drains, if you overcurrent the device, it blows up. And that's kind of the bottom line. You know, same is true for the input. If you overdrive it, there's only a few different things that you can do to kill one of these LDMOS devices, and too much voltage, too much current, too much heat. That's the long and short of it. And when your SWR shoots through the roof, it can do any one of those 3 things. It can give the device too much voltage, too much current, or too much heat. And too much current leads to too much heat, so it's kind of one of the same thing. It's all on the same thing. SWR, you know, it's not necessarily going to be directly related to voltage and current. You can have a really high standing wave ratio, but the voltage is low. You know, it's a matter of how much power is coming out of the device, how close it is to the voltage limits, how much heat it's absorbing. Yeah, I mean, everybody I know that's worked with LDMOS has blown one up from bad SWR. It's just, that's how it goes. If you turn down the voltage, so the voltage coming into the pallet, if you turn that down and you turn down the drive level, you can start doing stuff like BBI's video where he's arc welding with it. You know, I to be honest, I've never even seen his pallet. I don't know what he did, but I know he wasn't running the thing full tilt for that video, and that's because if you do, there's a much higher chance that it's going to blow up. You know, you drive it harder, you run it with a higher input voltage, and it's much more likely to blow up if there's a failure in your output somewhere. And yeah, that's my opinion on it. LDMOS is not indestructible on the output. It's not. I've seen it time and time again. You know, you can't do that at full tilt. It doesn't work out. Maybe in laboratory conditions on NXP special test bench it works, but in real world application it doesn't always do it. So when this transistor blew up, that one survived, and that's the original transistor. So it's kind of a weird situation. It's like, you know, this one survives but this one doesn't. So maybe this one got too much voltage or too much current and that one didn't. I don't know. When these things blow up, it's usually a mystery because there's no evidence left to figure out what happened. But I digress. The box is all back together. If you guys haven't seen them, these are my input splitters. Pretty simple stuff, just a shunt capacitor, series inductor, and then one of these little common splitters that you see in 2879 amps. They work great. They have good isolation, good impedance match, so 50 ohms in and then two 50 ohm ports out. Real simple. I just made a PCB so that I could mount them in convenient locations and stuff like that. And I'm not going to go over the pallets. You guys have seen all of this. Over here is my fan switch. So this is one of those little temperature switches I mentioned earlier, and it's just there to shut the fans on and off so they don't run constantly, because I can't stand it when the fans are on for no reason. So as soon as the heat spreader gets up to 45 degrees Celsius, the fan switch kicks on and turns on this MOSFET, which provides power to my fans over here. I need to add another one of these for 100 degrees Celsius in the same spot. So this is right up against the spreader here is a pretty good spot to put temperature switches. And a good one for over temperature is about 90 or 100 degrees Celsius. If you put a switch like that right here, it makes a good over temp. So, you know, if this was a 100 degree switch, it would be great to connect to your relays so that the relays shut off if that temperature gets too high. And that's what I'm going to do. I'm going to take another one of these switches with the proper rating and probably put it over here and use that switch to disconnect the relays and disconnect the bias and all that if the temperature gets too high. I'll probably never hit it because, like I said, I'm not real long-winded, but never hurts. Both the boards have the output filters on them, and those are going into a combiner. So this combiner is really simple. It's two pi networks, a shunt capacitor, a series inductor, and then another shunt capacitor on the other side where the two ends meet. And it's a really simple combiner design. It works freaking fantastically. When this transistor blew, the other one was still running, and it blew out these resistors here, so I had to replace those. But they did their job. They generated a little bit of smoke, like BBI says. You know, I only used a bigger resistor because it makes more smoke. I totally get what he's saying, because if you wanted that resistor to withstand a total imbalance between these two, it would have to be one hell of a resistor. You know, I think that resistor would have to dissipate half of the power from the pallet. So, you know, that'd be a pretty serious resistor if you wanted to run this with one of these pallets turned off. But they did their job. They made a little bit of smoke, and yeah. Now that everything's back together, everything seems to be perfectly well balanced. All I did was take the old transistor out, put a new one back in, and it's good to go. Oddly enough, these are mismatched lot numbers now, because I didn't have that lot number over there. So these are mismatched lot numbers, and I was a little concerned about how that was going to affect the balance. And truth be told, I'm seeing a couple 100 watts less on the watt meter than I was before, but I'm not seeing any heat in weird places. Like if you look at this with the infrared camera, there's no heat in the resistors over here. This transformer is just as hot as that one. You know, it's not imbalanced. I think it's just not quite as perfect as it was, and it's not making quite as much power as it was. But that's the way it goes. So yeah, that's pretty much how it's done. So if you notice, the way that I built this box is kind of in a modular fashion. I've got a combiner PCB that's built all by itself. I've got a splitter PCB. I've got the pallet PCBs. Those are kind of like modules, and you put them together like Legos. So the only downside to doing that is if there's any mismatch in your relay or in your input or in your output, you're going to have to modify the tune on the input splitter or the output combiner. But if you hook up your relays correctly, they will not cause enough of an impedance bump to be a problem. And if you notice, these relays don't have any tuning capacitors on them. They are not creating a big enough impedance bump to cause a problem, and that's because of the way that they are wired. Let me get in here and see if I can show you kind of how that's done. I actually been meaning to make a separate video on this altogether. So this is the actual input coax. This goes over to the input. So if you notice, the coax is shielded as far as it can go. I don't have any long unshielded wires hanging out here. The only unshielded portion of this is these two wires here, these contacts, and then it's right back over here into a shielded coax. What's the matter, bud? I'm making a video, bud. Can you go play outside?
Puppy, don't let the puppy eat your sunny.
My kid popped in to say hello. So if you take a look at this relay, the unshielded portion of the connection is minimal. Like, it's shielded from here to here, and then everything in between is the only portion that doesn't have any shielding. And that's to minimize the inductance. You know, as soon as you start taking the shielding off of these wires, they become inductors. And, you know, maybe even weird transmission lines. Maybe they have capacitance to something and they're like a weird transmission line. Bottom line is, you take the shielding off and these wires start to act weirdly. They don't present a 50 ohm impedance anymore. So you want to minimize that. Anything you can do to do it is a good thing. So even without tuning capacitors, the pass-through tune on this relay is like 1.2, which is totally acceptable in my book. You know, maybe somebody out there is going to be finicky about it. Oh, 1.2, I could get it down to 1.0. Yeah, that's cool. You're probably not going to get anything in return for it. Yeah. You're not going to hear anybody you didn't hear, and nobody out there's going to hear you when they didn't before. You know what I mean? Not a big deal. But then again, you know, every little improvement that you make all adds up in the end. You know, it's like getting your antenna tuned perfect, getting the right coax that doesn't have a whole lot of loss. You know, every little detail adds up in the end, but any one particular detail in the middle is not going to, you know, make or break you. So that's my philosophy about it anyway. If you're a comp guy, maybe you want to nitpick every little detail, but I just like to talk on the radio once in a while. And the same thing is true on the output relay. Exact same setup. You know, the wires are as short as possible. Coax is shielded as much as possible. And the little impedance bump that this presents wasn't bad enough to change the output power of the pallets. You know, they're still making a good solid 2 kilowatts a piece, PEP or CW. But yeah, almost done. Got to plug a hole. Got to add a thermal shutoff sensor somewhere, and that'll probably call it done. Anyhow, guys, thank you for watching. I hope you enjoyed the video, and I hope you enjoyed getting to take a look at this box. Like I said, not my finest work, but it was definitely a very fun project, and it works, and I can't wait to run it, and it's probably going to end up in my mobile one of these days, but we shall see. Anyways, thanks for watching, guys. I'll catch you next time.